So in this part of the lesson, we're now looking at the steady flow energy equation. In the previous lesson, we're discussing the non-flow energy equation. One thing we established was that in a non-flow energy equation, you're looking at fluid that is confined within the boundaries we set within the system, so it does not move. But steady flow gives us the opposite of that. So we're supposed to see this working substance now moving across the boundaries. And hence, let's see now how we can analyze this steady flow energy equation. So the first thing we're going to do, so let me just keep it first of all in a different mode. Okay. So here, one thing you'll notice is that when you are considering the steady flow energy equation, the principle is that the total energy remains constant. Now, the various forms of energy involved. Of course, one thing you'll notice is that when we say flow, for movement to take place, we expect kinetic energy to be involved. But aside from that, we also have other things that are important. If you look at where we're coming from, we already discussed the importance of internal energy, which is the very first one here. So we have internal energy as one of the energies involved. There's also pressure energy. Basically, this is a kind of energy which could also be responsible for forcing the fluid to flow. But we will consider it as pressure energy. Then we also have the velocity energy, the energy due to the motion, that is kinetic energy. And remember, the topic is thermodynamics, so we cannot ignore the heat. So here we have heat energy. Then interestingly, we also have the potential energy. Now, according to the steady flow energy equation principle, all these energies, when added together, they have to remain constant, meaning that the total energy at one point should remain the same when this fluid moves from point A to point B, and so on and so forth. So writing now in mathematical form, internal energy is represented by letter U, so that's U1, because that is state 1, the internal energy at point 1. Pressure energy, this is now supposed to be a product of the pressure, and not just the volume, but we'll say specific volume, because this is volume per unit mass. Then we also have the kinetic energy. Kinetic energy, the formula is half mv squared. Now, in this case, the mass is equal to 1 kg. And hence, you have, in place of v, we use this letter c. So that's why we have c squared over 2. Where is the mass gone? The mass is 1 kg, so it has been swallowed up. We just remain with c squared divided by 2. Heat energy is represented by letter Q. This is the one we have here. Potential energy, we know that the formula for potential energy is mgh. We don't want to use h because it will be confused with another factor we'll soon look at. So that's why the formula simplifies to gz1. So now, when you say this is constant, it means when we consider two positions, position 1 and 2, the total should remain the same. Meaning, when this particle, when this working substance is at point 1, initial internal energy is okay, that's U1. We have P1, V1, then there's C1, which is velocity 1 squared over 2, added to heat energy, and then that product. In the second state, when it goes out, or at point 2, which can also be point B, we write the same factors, but because this is now position 2, we insert the 2. So internal energy number 2, pressure 2, specific volume 2, velocity number 2, velocity represented by letter C, squared over 2. Then the only thing you need to take note here is this. Let me just get a pen. Okay, it's a pointer or a pen. So here, we're saying that the heat energy now turns into work, but the potential energy remains the same. But this time we take 2. Instead of this one here, this becomes 2. So that is how we start. And we don't end there. Look at this. Here, when we're dealing with this type of, this form of energy, you will notice that here, GZ1 is involved because this is representing the potential energy. But if you look at the kilojoules of energy, the energy amounts that we're going to consider, this potential energy is quite small compared to other forms of energy. So it's negligible, meaning in our analysis, we are allowed to neglect it. It can be neglected. Some odd books, they've tried to maintain it, but the end result is this is negligible. So when you remove this factor from this equation at this point, you remove this and you remove that because it's almost equal to 0. Then what you remain with is these other ones remaining here. So you have U1, P1, V1, C1 squared over 2, and heat energy here. On the other side also, everything is maintained and up to work. So this one you're seeing here gives us one form of the steady flow energy equation. Sometimes we may use it at this very point, but we still have room to make improvements to this to simplify it further. So here comes in a factor known as enthalpy. Enthalpy is defined as a sum of the internal energy and the product of the pressure and specific volume. Now here we've used small letter h because this is internal energy per unit mass, or we can call it specific internal energy. So when you look at this, the rather is enthalpy. So the enthalpy that we have here, it represents the sum of the first two items here. So U1 plus P1, V1, the whole of this, everything you're seeing here, to be represented by what? By internal energy H. Now, because there are 2, you say H1. The same thing with what you have right here, to be represented by H2. So, meaning that when this is simplified, everything here there should dissolve. You should have H1 plus this and that. And hence, there we have it. So then you end up with H1 plus C1 squared over 2 plus heat energy plus H2, equals H2 plus C2 squared over 2 plus the work done. This now ends our steady flow energy equation with the enthalpy now incorporated. So that is our conclusion, saying that this is our steady flow energy equation applied in an open system. This is no longer a closed system because the working substance is now moving at a given velocity with the pressure and the other factors taken care of. Yes, now here we're just trying to emphasize that U represents internal energy, P is pressure, V, whether this is letter nu from the Greek letter known as nu, and it represents specific volume or simply volume per unit mass. Then C is velocity. We could not use the V because it might be confused with this other factor here. So this is the one we're going to use. But aside from that, we also have one other factor continuity of mass flow. When you're talking about continuity of mass flow, you're actually trying to say that the amount of mass flowing through or passing through a given point remains constant. Meaning that whatever mass is entering a system or entering a particular point should be equal to what is going to leave. Unless you have a leakage or some disturbance. That is continuity of mass flow principle. And it's better off expressed in form of this expression where we say cross-section area times the velocity is equal to mass flow rate multiplied by specific volume. And here you may decide to make mass flow rate the subject of the formula. Mass flow rate is equal to area times the velocity divided by specific volume. Your answer here will be in kgs per second because this mass with a dot means the rate at which the mass is moving. So it will be in kgs per second. So there, just add more emphasis that actually m with a dot on top represents mass flow rate, then c is the velocity. Then the cross-section area of flow, A in square meters, that's A, that is the area. Okay, now, how can we apply that into some examples? Let's look at example number 1. In this example, we've been given this scenario. Steady flow open system, fluid substance flows at a rate of 4 kgs per second. It enters the system at a pressure of 600 kilonewtons per square meter and velocity 220, internal energy 2,200 kilojoules per kg, and specific volume 0.42 cubic meters per kg. Then when leaving, the pressure is 150, velocity 145, internal energy 1650 kilojoules per kg, and the specific volume 1.5 cubic meters per kg. So this is the information that we've been provided. Now, it doesn't augur well to just go straight and start solving the problem. Let's fish out this information, arrange it into some data, so that when we now pick which formula to use, it will be much easier. So, question number A is asking for us to calculate the inlet and exit areas, and B, the power. And then we say where this power is to or from the system. Let's go back to the data. And before you even go to the data, here you can see that we have two sections. There's one where the working substance is entering. Then the other part is where it is also leaving. So as we write down the data, all this information we have here should be put together to make sure that we can account for the fact that this information remains on the side of the inlet or the entry section. Then this other information below here should be for the exit side. Unfortunately, this one, according to the continuity of mass flow rate, it will remain for both sides because the mass entering must be equal to the mass leaving. So what is exiting and what is entering, the flow rate remains the same. So we will still maintain the 4 kg like that. Look at our data here. So there, in fact, we started with the same. The mass flow rate is 4 kg per second. But let me pick up the inlet. On the inlet side, the first thing you have is pressure 1. We're going to maintain this pressure in kilonewtons per square meter, meaning that all the other units will try to make sure that we keep them in kilo SI unit. So we have C1, 120 meters per second. We also have internal energy number 1. This is 2,200 kilojoules per kg. Then we have specific volume number 1, which is 0.42 cubic meters per kg. All this information belongs to only the inlet section, the entry section, the initial section when this fluid is just coming into that system before it can exit. What about, all right, we also have the heat. The heat energy, what we've been told, let me just quickly go back to the question. It says the substance has a loss by heat transfer of what? This much, 40 kilojoules per kg to the surroundings. Heat transfer, when heat is leaving a system, we said it carries, or is supposed to carry air. It means that system, that amount of heat is considered to be negative. If the heat has been received, then we consider that heat energy to be positive. But in this case, the heat is being rejected, it's leaving the system, it's heat loss. So it's negative heat energy. So that's why, from what you can see here, the Q presents negative 40 kilojoules per unit mass. Let's then go to the exit section. In the exit section, we have pressure number 2, 150 kilonewtons per square meter. Velocity number 2, 145. U2, 1650 kilojoules per kg. And specific volume number 2, 1.5 cubic meters per kg. So then, let's pick up the first part of the question, which is asking for the inlet and exit areas. So here we are going to use this expression that we started with, but we cannot use it like this because according to the continuity of mass flow, these remain constant. The amount remains constant. So what we are going to do is just to tell her this, the mass flow rate is the same, by specific volume, the cross-section area flow, the velocity, these will change. So we'll alter them. For the inlet section, we'll use 111. Only for these. We cannot do it for this one because this one is constant for both section 1 and section 2. So with this in mind, we can now just do the substitution. We're given the mass flow rate as 4 kg per second. The initial internal energy, the internal energy at section 1, or rather the specific volume was 0.42. Velocity number 1 at entry was 220 meters per second. So that's what we have. When you enter this in your calculator, it gives you the area as 0.007636. Let's duplicate this now with the exit section. With the exit section, we can even pick it up from this point, where area 2 is equal to mass flow rate by specific volume 2 divided by velocity 2. Then we can just substitute. The mass flow rate was 4, specific volume was 1.5, area 2 was 145 meters per second. So when you enter this once again in your calculator, that's what you should have. Now, let me emphasize here. Sometimes, according to the way information has been provided, you could even be given both areas, but the question perhaps is asking for the velocities, noticing that these velocities, you need them in the calculation now for the pressure, for the work done, and later on be power. So whatever you are given, you just come back here and make it the subject of your formula. Then you proceed with your working. So this is how you get the areas. Basically, we are looking at this formula and making the subject of the formula the two areas. Okay. Now let's proceed then to part B. With part B, we're now applying the steady flow energy equation. This is the equation we are going to use. We cannot use that one for enthalpy because it may require that we do the data and calculate this separately, even here. But why would we start doing that? We can just do the substitution. But we have a problem. If you noticed, internal energy was in kilojoules. Pressure was also in kilonewtons per square meter. The heat energy was negative 40 kilojoules per kg. Everything kilo. But when you look at the velocity, it was in meters per second, meaning that the kinetic energy per kg that you calculate here is not in kilojoules. Let me repeat that. All these factors you see here, they are all in kilojoules. All of them. The internal energy, the pressure energy, including the heat energy. Whether section 1 or what you have even this as section 2, including, of course, we'll find the work later. All of them are in kilojoules, except this thing you're calculating here, which is the kinetic energy for 1 kg. So what do? We need to convert this from joules per kg to kilojoules per kg. If your memory serves you right, you remember that when you are converting any normal unit from the actual SI unit to kilo, that SI unit, in this case, we want to convert from kilojoules, or rather from joules to kilojoules. The only way out is to divide by 1000. The only way out is to divide that by 1000. Meaning, if I have maybe 20,000 joules, to get them to kilojoules, then I'll divide that 20,000 by 1000, and I end up with 20 kilojoules. So that's what we're going to do there. If you have to divide this by 1000, it means you have C1 squared over 2 times 1000, or the whole of it divided by 1000. So here's the thing. Here you will notice 220 was the initial velocity, the C1. This 1000 you are seeing here is helping us to convert the joules per kg to kilojoules. The rest of them are also in the same kilojoules. Having said that, we can proceed with the rest of the substitution. Internal energy number 1, which is U1, was given as 2,200. Pressure 1 was 600. Specific volume 1, 0.42. And the heat energy was negative 40. So there we are. That is for the first part. And we continue. Even here, we introduce the 1000 for kinetic energy to confirm and to ensure that we can convert it from the joules to kilojoules per unit mass. The rest, we just substitute. The internal energy number 2, 1650. Then pressure energy, a product of the 150 kilonewtons per square meter by the 1.5 kgs, rather cubic meters per, our unit, our specific volume, meaning cubic meters per unit mass. And we're looking for work, so we will not calculate that work. We'll just leave the W like that because that's the one we need to find at the end of the day. So once again, I emphasize, the 1000 you're seeing here is basically for converting the unit to make sure that it aligns with everything here. So for those of you who like playing around with these numbers, you can decide to convert these other units to joules per kg. Then you don't have to put this 1000 here. Meaning from your data, the 2200 kilojoules, you multiply by 1000. Even this by 1000, even this by 1000, even this by 1000, even that by 1000. So you can see converting 1, 2, 3, 4, 5 factors instead of just putting the 1000 on 2 positions. You'll notice that other part can be quite long, and when you involve such lengthy work, it exposes you to easily make a mistake along the way. So this is smarter because you know that your end result, your final answer, will also end up being in kilojoules. So what happens? When you enter this in your calculator, making W the subject of the formula, this is what you find. But the question did not ask for work. The question was asking for power. So with work per kg being given, you can now say power, you multiply the mass flow rate by the work that you found. Then the kgs will go away. Then you end up with kilojoules per second, which is like kilowatts. So we bring them back. The answer we have multiplied by the 4, and we have 2,202.75 kilowatts. That is our answer. Again, the question was also asking us to verify whether this work is coming from the system or entering the system. One thing we established when we were looking at the non-flow energy equation is that a system must do work. A system is supposed to do work, meaning there has to be a work transfer from the system, or in this case, it's power transfer. The way they behave is the same. Power transfer must be from the system. Then we will say this is positive. If, like in a compression process, power or work is being wasted into that system, then it's negative. So since this is a positive answer, it means our power is coming from the system. So that's our explanation right there. Steady flow energy equation. Let's pick up another one where we can see a scenario where this is going to be used. It has been combined, and we're making use of enthalpy. So here's example 2. Example 2 says air enters a turbine system with a velocity of 100 meters per second and receives 140 kilojoules per kg of heat energy. On exit, its velocity 75. Enthalpy is increased by, let's get this very clear. It's not saying this is a final or initial enthalpy, but it's an increment. Then the rate is 2.5 kgs per second. So the question is, determine the power that has been developed. Our information. Velocity number 1 is 100 meters per second. Heat energy. Let's check again. It says it receives this amount of heat, meaning heat received, we say it's positive heat energy. So it remains like that. Q equals 140 kilojoules per kg. Velocity number 2, 75. This time we haven't even separated them because the list is not that long. So it's easy to put them together like that without confusing them. Now, here, when the question is saying it has been increased by that much, it means the exit enthalpy is bigger than the initial one. By how much? By what they have given us there. Subtract any two numbers, H2 minus H1. The answer you should get is the increment, the 330. So the smart move is to make one of them 0. In this case, we want H1 to be 0, then H2, 330. If you subtract them, 330 minus 0, you still end up with a 330. So meaning that your H1 is 0 and H2 is 330, because the difference between them, H2 minus H1 is the 330. Let me go through that again. The question did not say this is our final or initial. It said this has been increased. How do you detect an increment? You subtract the final item you have from what you started. So final enthalpy minus initial enthalpy gives us the increment or the change. And since it's an increment, that change is supposed to be positive. So hence we have it that way. Now here, to make use of the equation the way we developed it, I decided to split these in the data. What is the H2 and what is the H1 to fulfill this condition? You will notice that H2, if I put 330 and put 0 there, this will be true. So that's why we're saying H1 is 0, H2 is 330. You can use any other numbers as long as when you put them here, they do that. But I always encourage you to make use of the 0. If by any chance the question had said this is decreased, then we're going to swap this. You have 0 for H2 and the other one for H1, because a decrease should have ended up with a negative value there. So for this question, that's the part where you need to be very careful. Mass flow rate we've been given is 2.5 kgs per second. Now here's our solution. We're using the shortened version of our steady flow energy equation, the one we ended up with, which gives us KE, enthalpy, heat energy. Repeated there, but where there's heat, we end up with work on the exit side. So we can do the substitution. This is 100 squared divided by 2 by 1000 for converting purposes. In our data, our H1 is 0. Then heat energy, it's an increment in heat, rather it's heat received. It was 140. On exit, we do the same, 75 squared divided by 2 times 1000. Plus H2, which is 330, again added to just the work done. So here, our task is simply to make work subject. When we find it, we complete with the last part. Then, when we make work the subject, you will notice that it will take us now to finding this one. Unfortunately, this time around, our work is negative, which is very normal. The question was asking for power, so we cannot end here. We push up the last part. We say power is supposed to be a product of work and the mass flow rate. So I'm saying power is a product of work and the mass flow rate. Work done per second, whether work done per kg multiplied by the flow rate, amount of kgs flowing per second. Then what you end up with has to be in kilowatts. So the mass flow rate was 2.5 kgs per second. Work we've just found it as negative 187.8125. Whichever version of calculator you're using, when you enter these, you should have negative 469.53125. Here, I still encourage that for the final answer, you can still maintain 2 decimals, but I just wanted to be a bit more generous, avoiding noticing that should anyone want to use this number elsewhere, it will be safe. But for numbers where you need to use them somewhere else, I always recommend you maintain minimum 3 decimals, then okay. Okay, so that's our answer there. And sorry, let me just check up the conclusive part. The power developed. So this power developed, that's what we have. Now here, the question did not ask us to interpret the answer. If they were requiring us to interpret, I think that's what I wanted to add, but later on I realized it's not necessary. If they were requiring us to explain whether this work transfer, the power transfer is from or to the system, it would have meant this is power into the system. It's like a compression process. That's why the power developed is negative. For now, this is our power, and here's our exercise for the sake of trying out. You can take your time, solve these 4 questions. Should I have any problem, you know how to catch me. You can always get in touch or put your question, clarification in the comment section, or definitely get back. Thank you very much. And for now, I'll end here.